Okay, I'd like to thank Owen and Francis and Anthony for this opportunity, and obviously the MacArthur Foundation for the ability to come out here and talk. Anthony covered a brief sort of overview of episodic memory. I'm going to narrow down even farther into episodic memory. As you can see, there's a lot of topics that you could discuss in episodic long-term memory. I'm going to be focusing on episodic recognition memory. That is the ability to say that a person or a stimulus was an element of a prior experience or encounter. To say, yes, I recognize you from a prior encounter that I had with you. Okay. And what I want to do is to try to sort of discuss a little bit. Oh, by the way, I am not an expert on eyewitness identification. So that's an applied sort of phenomenon. I am a very geeky, basic research sort of scientist. Hopefully some of the things I talk about will definitely inform that area, and I will cover a paper that has recently taken a fairly sort of geeky laboratory measurement approach to this problem to try to say something about sequential versus simultaneous lineups. But again, I'm going to be looking at episodic recognition memory and trying to help you understand the distinction between discrimination or discriminability that an observer has between things you've experienced before and not experienced before, and bias, and how we try to separate out judgment bias from the accuracy of the observer. Okay. Before I do that, I'm going to step back and take a little bit of historical perspective. So a lot of the ways in which Anthony was talking about memory, the idea of different representations, different processing streams, different skills that people have, came about as something that we in psychology refer to as the cognitive revolution, where we were freed from the strict behaviorists and we were allowed to talk about the inner workings of the black box. And in particular, we were informed by using analogies that came out of artificial intelligence, linguistics, and other sort of disciplines as we sort of coalesce together to start thinking about the human being as an information processor, and to use different sorts of analogies to make predictions about the way people process the world. And one analogy we used, and we still use today, is the computer analogy. That there are analogs between the way computers work and the way human beings work in terms of input and output systems, processing bottlenecks, different types of representations. So you'll often hear people refer to working memories Anthony discussed as very similar to the way your RAM operates in your computer. It's a very small sort of memory component. It doesn't hold a lot of information, but what it does hold is immediately accessible, and so you can work with it, manipulate it. That end-back task that Leslie showed yesterday is a nice example of that. You have this information online that you're working with it, but we also have a long-term memory that has a huge capacity, and you can think of that as in terms of your hard drive on your computer. Right? It's content addressable. It seems almost inexhaustible, although hard drives are never inexhaustible. Most of you know that you start adding more and more and more, but it's slower to retrieve. And so those sorts of distinctions, those sorts of analogies, I think helped us quite a bit in psychology. Another analogy that's not quite as well known has to do with this particular problem. Coming out of World War II, both in terms of the receivers themselves and the operators sitting at the receivers, how do people separate signal from noise? How do they make that judgment? So this operator, how does he make a judgment that that is in fact an enemy, say, missile coming in, versus that's just clutter from the sea or clutter from the environment? And more specifically, how does that observer shift their bias such that obviously if you're in a wartime zone, you want to actually sort of favor false alarming to stimuli as potential threats or targets, whereas you're in a peacetime environment, you want to use a different standard. So how do people do this, and how do we design a receiver that would be able to make these characterizations? And so this analogy that people started to use was to say human beings and receivers to some extent make decisions based on statistical properties of the information they're working with. They are sort of like an informed statistician dealing with a noisy environment. And hopefully I'll unpack that a little bit better on the next slide. The first paper to come out and use this and create this theory that I'm going to be talking about, called the theory of signal detectability, what we call signal detection theory now, was written by Pearson, Birdsall, and Fox, and it's impenetrable. But what it's basically, unless you want to go back to high school or college and revisit a year of calculus, it's hard to get through. I've attempted several times and just went and had coffee and given up. But what's interesting about this paper is they're very, very agnostic about the term receiver. In other words, they use the term receiver to apply actually to receivers, but also to human beings, because they don't make any distinction about this decision problem. It's the same decision problem in their eyes, and so they're very agnostic. Fortunately, psychologists got a hold of this work, psychologists with some statistical and math skills, and translated it into the realm of human performance. And so the initial idea by Tanner and Birdsall, Sweats out of MIT, I believe, was to say, look, This is very analogous to what people face when they make perceptual decisions. They're faced with noisy environments, the stimuli give noisy signals, and the question is whether or not there was something there or there's nothing there, and how we get this discrimination problem. A little bit later on, as we got into the 60s and the 70s, theorists actually said, well, wait a minute, this is actually also like a recognition memory problem. You have stimuli that are familiar and stimuli that are novel, and the question is how do you distinguish between these two states, and how do you bias or avoid biases when you're making these sorts of judgments? So what does this theory, this signal detection theory, allow us to do? Well, it starts to allow us to answer some basic questions like, one, why do recognition memory errors occur? We've run hundreds of thousands of recognition memory tests in my laboratory. I have never, if you run a list long enough, I have never ever seen a subject not commit errors in recognition memory. The percentages can be small, but it's almost impossible not to commit these sort of confusion errors between things you've studied and things you have not. What are the consequences of biases and strategies during recognition judgment? Something that psychologists are generally interested in is how can we rank observers in terms of their accuracy independent of any potential for bias, right? Because different people have different proclivities to sort of say, yes, I recognize that versus I don't recognize that. Just as when you go into the eye doctor, you may really wish that your visual acuity was good. You may form various strategies to try to outwit the eye doctor. And what the eye doctor really wants is a test or a theory that allows him or her to isolate your discriminability of visual stimuli from your desire to try to cheat the test. And that's what this theory allows us to sort of do. And something that I hope is interesting for this group is, can you use these sorts of models to differentiate between different procedures as more or less accurate and useful for discriminating known versus unknown targets? Since it's almost impossible for me to talk about anything without talking about my own research, I will try to creep in at the back end a couple of studies in which we actually purposefully bias people to see how they use environmental cues to inform their own recognition judgments and try to boost their accuracy in the laboratory. So I've talked about this revolution. Yes, we're going to view the observer as making a statistical judgment or as an informed statistician making a judgment, sort of as an analog. But I haven't shown anything sort of to connect to that idea. And so here's a statistical problem. Say we have a set of test scores, and we suspect they may have been inflated. Like you could think about mandatory testing or all sorts of environments where people are worried about the purity of the test scores they're looking at, and say we think they may have been inflated by, say, adding 5 points to each score in the sample. And the question is, how do we decide whether this particular set of test scores were tampered with or not tampered with? This is what's known roughly as the Neem and Pearson problem, and the statistical model is the Neem and Pearson decision model. And what you have here is you have essentially the set of samples you would expect if they were not tampered with. Right? You have this distribution of samples that you should get, sample means that you should get, and you have a separated distribution by 5 points of the set you might expect had they been tampered with. And what Neem and Pearson were able to figure out is essentially how should you place your decision criteria in your cut point to make these judgments about tampered or not tampered. And in the simplest sense, and I'm really basically oversimplifying this problem, is you should place your cut point to refer to things as tampered or not tampered right at the intersection of these two distributions. Right? And that tells us where our decision criterion should be if we're going to be optimal. Now this assumes a lot of things. This assumes basically that the prior probability of tampering is 50% for either thing. It also assumes that we think that the errors, these two types of errors, calling something tampered when it was in fact a clean sample, or calling something clean when it was in fact a tampered sample, are equally problematic. And these may not be valid assumptions. And I may have time to touch base on that later, but stripping those assumptions aside, this is where you want to place the criterion. And this particular criterion will maximize your tendency to be correct over the long run. Right? Not on any given sample you don't know if you're correct, but over the lifetime of making these judgments, you would maximize your tendency to be correct. Now, whenever I used to read this and people, and I talk to colleagues and we say, yes, this is where you want to put the optimal criterion, I used to nod my head a lot and go, yeah, sure. I really, whenever I look at it and go, I don't understand necessarily why by looking at that figure, and I'm not going to work through the calculus again to figure it out either. But geometrically, you can kind of see this point. What if instead you were what we call liberal biased? That is, you shifted your cut point to the left and you decided to call more things tampered than you normally would. What you can see here is there's a benefit, there's a gain. You detect more of the items that are tampered. This area under this segment is your benefit by shifting your criterion to the left. But the problem is that you're also much more likely to call things that are clean tampered, right? Which is another type of error, and that's this area right here. That area is larger. So the net of shifting to the left drives your overall performance down. And this is true for any other point away from this midpoint. It always drives your overall performance down. Okay, so how does this get back to the idea of, say, face recognition? And the insight of detection theorists is that this same decision model could characterize an individual trying to isolate or separate individual perceptual or memory experiences. So say you're at a cocktail party, you meet a bunch of people, you have a bunch of novel faces. Before this party, if I just show you faces of people just like Anthony was showing you words, they will give you some sense of familiarity. Most people will strike you as novel if you haven't met them before, but some people will seem familiar to you. So there's a range, an a priori range of familiarity that we have for faces, even the ones we haven't met. If they're introduced at a cocktail party, the model essentially says this is a new distribution of faces that have been shifted to the right, and they're now familiar overall, but there's a range of variability. And so you could call these sort of the brief acquaintance experiences of recognition strength that you would have. I ask you, I'm going to show you a list of people that are either new or people from the cocktail party, and you need to say, yes, that's somebody I met at the cocktail party. The idea is that you place this criterion here, and you generate these, this confusion matrix of responses that you can have. And this is where it gets even slightly more jargony, and I'll try to sort of make sure I'm unpacking what I'm saying as we go through some of the later demonstrations. But you can either say, yes, the person was present at the cocktail party, and they were present. That's called a hit or a detection. Or you could say they were absent, but they were present, but they were in fact present at the party. That's called a miss. You could say they were absent, you could say they were present when in fact they were absent, and this is called a false alarm, or we would be interested here with this notion of a false positive identification. Or they were absent, and you could say, yes, they were absent, and that's called a correct rejection. There's also different terminology used for the same procedure in the medical field. There's about 6 different terms that people use for all these cells, and hopefully I'll try to make it clear as we go through the terms I'm using. So these proportions, your tendency to commit these sorts of successful responses or errors, are governed by these areas under these normal distributions. And so the first question, why do recognition memory errors occur? Well, under signal detection theory, they occur because the information that we have to use is continuous and noisy. They're unavoidable. You will always make errors. The question is the trade-off between the types of errors that you're going to make. There's simply no way to get around it. But the next question is, what are the consequences of having a bias judgment strategy, right? Not using the optimal location here, but having a bias. And there are huge individual differences in the laboratory between biases in people. Some people are very biased to say they recognize almost everything. Other people are very conservative or cautious when saying they recognize something. And we still don't understand why those individual differences necessarily exist. Okay, so here's an observer whose internal resolution is quite good. The separation between the signals that are generated when they see something familiar versus novel is pretty large. And what we want to ask is, what happens as that person takes a very, very conservative or strict approach to calling something recognized to a very, very liberal approach to calling something recognized? And you can trace out the relationship between their detection rate and their false alarm rate or their false detection rate as a function of how strict or lax they are in judging something as recognized. And this traces out a function that we refer to as the receiver operating characteristic of that individual, right? And what this function shows us is your tendency to correctly detect as a function of your tendency to falsely identify, right? It's a sort of, what are the gains that you get relative to the errors that you commit for being strict or conservative? Here's a person that's much more like I am. Their internal signals between people they've met and not met are not separated by very much, right? And as they go from very strict to very lax, it traces out a function, but this function is lower, is shallower than this function up here. Okay. This receiver operating characteristic is the bias-free, the area under this curve is the bias-free measurement of accuracy. It is the statement of someone's accuracy regardless of where they position their particular decision criterion across all possible levels of conservatism they could display. Another way to think about this area is that is the probability that if I randomly sample an old item and new item and show them to you, that you will make the correct judgment. Right? So the area measure is what we really want when we want to say somebody is more or less accurate than somebody else. Okay, not only can the ROC be used to describe the relative accuracy of 2 different observers, but the other major insight of it, and the reason why it's so useful in the medical profession as well, is that it can be used to rate the relative accuracy of different diagnostic tests, say in the medical field, or different procedures, say lineup procedures. In other words, you can now treat the unit of analysis not as an individual and compare 2 individuals, but as a test type or a test procedure and compare the 2 test procedures and look at the ROC of the 2 procedures. Now the only trick here is that there's a shift here. Before, and the way most signal detection theorists talk about it, we're worried about the accuracy of individuals. And so the comparisons between me and you as an individual and the separate trials of an experiment, say the 300 times I show you new and old faces. When you move to procedures, now the procedure is the unit of analysis, and the trials are the individual statements of observers saying, yes, I recognize that suspect and I'm highly confident, or I don't recognize anybody from this lineup and I'm highly confident. Right? So those are the trials. So people are no longer the unit of analysis, it's the test procedure that's now the unit of analysis. The only other thing I want to sort of point out before we actually get to the paper is that under this framework, it's important to always go back to the point that percentage correct, our natural way of thinking about accuracy, is not particularly informative. So if I look at your percentage of correct judgments, it doesn't really tell me much about your overall discriminability capabilities. And you can see this here with this particular observer and this ROC. Here, the person is very, very cautious, and they call almost everything new, unexperienced. But their percentage of correct is necessarily about 50%, because half of the things are new and half of the things are old. If they're optimal in their criterion placement, they get about 75% of the things right. But if they are super liberal, they go back to about 50%. But this is the same observer with the same capabilities. They just have different strategies. So the percentage correct is not very informative when you're talking about somebody's accuracy, counterintuitively enough. Okay, so how do we actually examine this? What we do in the laboratory, or what we do when we look at these different sorts of procedures, is we use confidence as a proxy for where this criterion location is. So what we want to look at is the idea that people's most confident endorsement represents the highest sort of criterion they would have used. And then we plot the first hit rate relative to the first false alarm rate that we would observe. Then we say, oh, let's take their medium confidence responses and look at the cumulative data to the right of this. Anything that was endorsed with a medium or higher level of confidence. Then you take their next level of confidence, and so this is how you actually trace out the empirical ROC for an observer or a procedure. How well does this actually do? Pretty well. So this model actually works quite well. And this is actually recognition data for people and their ability to remember odors after either 1 week or a 10-minute retention interval. And you can see that the actual points of the observer trace these theoretical arcs quite well. Right? So there's this nice match between the model and the actual performance of people. Okay, so how does this relate to the actual question of interest here? Mickey's, Flo, and Wickstead were very interested in this phenomenon and saying, let's use the receiver operating characteristic to look at the different sequential versus simultaneous lineup procedures to see which one yields the greater discriminability between targets, target present and target absent lineups. Again, now that it's the procedure itself is the unit analysis, and what we're looking at is we're going to collapse across individuals making single identifications and look at the two procedures. These are the 4 possible situations you could find yourself in. Okay, as a subject, you can either be in a simultaneous lineup with the perpetrator present, a sequential lineup with the perpetrator present, simultaneous perpetrator absent, sequential perpetrator absent. These are the potential situations that could lead to false alarms. These are potential situations that could lead to hits or correct detections. This is obviously very important because there's quite a bit of debate about the relative utility of sequential versus simultaneous lineups. And in the Mickey's paper, they make a fairly strong argument. I think a brief review of the literature shows that the general assumption was that the sequential procedure is superior, yields better outcomes, is more accurate than the simultaneous procedure. And this push to get people to be more willing to adopt the sequential procedure. The only thing else sort of is a caveat here. One can't really safely, so the take-home point is you can't compare the accuracy of 2 people, 2 tests, 2 procedures without collecting a full ROC. We don't do it because it's time-consuming, but you really have to do it. The only case where you don't have to do it is where one procedure yields a higher detection rate and a significantly lower false positive rate. There, it's not ambiguous which procedure is better, but that almost never really happens in real practice. Usually, they tend to go in the same. The hits and false alarms go in the same direction. Okay, what do the data look like given the ROCs I've just showed you? It's pretty straightforward. This is 538 undergraduates. This is simultaneous line procedures with six members. And this is the hit rate accumulated across confidence. This is the false positive rate accumulated across confidence. The area under the simultaneous procedure is significantly higher than the area under the sequential procedure. So the simultaneous procedure yields greater discriminability across these subjects in these situations. They also moved to an internet sample to get a broader array of people other than just college undergraduates. Here the numerical pattern is the same. Simultaneous yields greater discriminability than sequential, but it wasn't statistically reliable. And in a final study, they wanted to look at a situation where they have unfair lineups. So in the target absent case, they actually picked one of the members and they modified them to resemble the actual perpetrator seen in the video. And here the numerical pattern, again, favors the simultaneous, but it wasn't statistically reliable. So the key take-home point from this paper, though, was that these data do not support this idea that sequential lineups are superior to simultaneous. If anything, they actually lead to the reverse conclusion. But there is a benefit to sequential lineups. If you look at these points here, what you can see is that they're generally shifted to the left on the x-axis here. And what that means is that the sequential procedure tends to yield a lower false positive rate overall, even though it is less accurate. And so this lets the question that they discussed in the paper, is an interesting discussion following the data, is this lower false positive rate in and of itself enough to recommend the sequential procedure? Because aren't we really worried about false positives? Their argument is no, because what you should be able to do is take the simultaneous procedure and give people instructions to make them more cautious, which should shift them down and lower their false positive rate, but you would still yield the benefits of having the better discriminability. My sort of argument is yes, because this is an empirical question of whether or not we can make people more cautious under simultaneous lineups. It's a lab question. I suspect it's going to be difficult to make people exercise more caution because when they have things arrayed in front of them, there's a tendency to want to select something. But that's an empirical question and we simply don't know yet. Let's see. Oh, so the last thing I was going to wrap up with is a couple of slides looking at some of the research that we look in the laboratories. We don't really understand how and why people adopt recognition biases. And we don't understand the degree to which they are aware of their own biases when they're making recognition judgments. So what we do is we give people standard study lists and in something we call the explicit memory cueing paradigm. So they study a list of boring words, but then at test, what we do is we tell them we're going to give you hints before each memory probe. And those hints are going to tell you whether this probe is likely old or likely new. And you should use those to benefit your performance. In other words, you should cheat. We want you to use outside information to inform your memory judgments. And it sort of looks like this. The computer will tell you, oh, the next word is likely to be old, and then the word comes up. In this case, what we see, this is a valid cue because anguish was actually in the study list. But the preparatory cue may be invalid, right? This says likely old, but the word was not on the list, right? And that's for old materials. Or an old cue, you can do that for cues that indicate you should prepare yourself for something that's going to be new. Or you can do what's the standard recognition test, which is I don't give you any informative cues before the words appear on the screen. What we see when we do this in the laboratory with undergraduates is that, perhaps not surprisingly, people can boost their accuracy quite a bit when they have these probabilistic cues in the environment. Their recognition judgment accuracy goes up. However, what's a little bit interesting about this is that given two people with the same level of baseline accuracy in the absence of cues in the environment, there are huge individual differences in people's ability to incorporate external cues. Some people are quite good at using external cues to modify their memory judgments. Other people are horrible at it. And part of the reason is that some people are essentially just horrible. They're not very well calibrated. They don't know when they don't know something. Their accuracy is fairly good, but their mapping of confidence onto their accuracy is horrible. And you probably all know people like this. They're definitely confident in cases when they absolutely do not know the answer. And they're definitely confident in cases when they absolutely do know the answer. It's not that they don't know, it's not that they're good at knowing or not knowing, it's that you have no idea based on their confidence whether they know or don't know. Turns out this is actually, there's a variation in this skill. We also know that left lateral parietal cortex is very sensitive to the discrepancies between your expectations about your memory and the stimuli that appear on the screen, right? So when there's conflict between expecting something to be familiar and it's not, or expecting something to be novel and it's not, there's a very large response in lateral parietal cortex in other brain regions. What's interesting is that the response the brain has to unexpectedly novel stimuli is fundamentally different than the response the brain has to unexpectedly familiar stimuli. It drives different regions that we think are engaged in different functions. And in particular, we think that when you encounter an unexpectedly novel stimulus, you drive regions that are associated with orienting to the external world, visual attention regions. When you encounter something that's unexpectedly familiar, you don't do that. That's counterproductive. You actually drive regions that are associated with explicit memory monitoring. So you're trying to resolve this ambiguity. We also know that lesions of the left lateral parietal cortex do not disrupt basic recognition abilities. So a person with a very, very large lesion sitting right here in the brain is perfectly able to discriminate the novel from the familiar. But in our paradigm, what they appear not to be particularly good at is using external cues to bias those judgments appropriately. Last piece of data. This is from a graduate student in my lab in her dissertation. We have always used these sorts of cueing paradigms under the assumption that people do this volitionally. I say, hey, I'm going to give you these environmental cues. I want you to use them to bias your memory judgments to benefit your overall performance. So have at it. What never really occurred to us is that people may not be able to stop themselves from doing this. So what we did in this paradigm was to give them a couple of blocks where they use the cues, and they would say, by the way, we prefer if you only rely on your own internal memory signals. Do not use this environmental cue to inform your memory judgments. Just ignore it. It's very, very important for us. It's very, very important for her dissertation. She won't be able to leave school if you let these external cues influence your reports. And so we intermix these blocks. On this axis right here, you can see what happens when people are not cued in the environment. Their tendency to call items old overall is 50%, and we refer to that as unbiased. They are an unbiased observer on average. If you look in the condition where we tell them, please use these environmental cues to benefit your performance, if there is a likely old cue in the environment, it increases their probability of saying something is old by 15%. If there is a likely new cue in the environment, it decreases their probability of calling something old by about 15%. So the question is, what happens when we tell you, stop, please don't do this anymore? What you see is it decreases their reliance on the environmental cues, but they are extremely far from eliminating their reliance on these environmental cues. So this is her first experiment. We are in the midst of about 5 experiments to beg, to plead, to pay people, to give them reinforcements, to do all sorts of things to stop them from doing this. And it appears as though people cannot stop themselves from doing this, and they don't know that they're actually doing it. So it may be the case that very early on in the processing stream, that once you have an expectation about the way a stimulus is going to be in the environment, you are essentially, in some sense, doomed to be biased towards that judgment, even when trying to restrict yourself from doing it. Thank you.